Good morning. Thank you so much for coming to our session. We're going to be talking about RabbitMQ and Kafka. I'm Zoe Vance. I'm a product lead at Pivotal for messaging. I work a lot with the commercial RabbitMQ teams, but also talk to customers about their messaging choices overall. I'm unfortunately off the grid, so if you want to contact me, that's my email. Would love to hear from you, any thoughts or questions following this talk.
Hi, my name is Madhav Sathe. I'm the platform architect based at New York. And that's it.
So the motivation for this talk is, as we hear this question a lot from customers, like when should I use Kafka and when should I use RabbitMQ? And it's a tricky question to answer sometimes because so much of the underlying architectural decisions are so different. And we really wanted to go deep and think about how we could give you all the answers that will be helpful when you're evaluating, this is the use case I'm in, this is the situation I'm in, which tool should I choose, and what are the big challenges that I should make sure my teams are prepared for. So hopefully you'll walk out of here with a sense of the two different tools, the benefits of both, the scenarios where you should use each, the challenges associated with each, because unfortunately all great tools have challenges, the building blocks behind RabbitMQ, the developer experiences associated with both. Madhav's going to do his first live coding, which is going to be exciting to break it up in the middle. And then we're going to talk about the building blocks for Kafka. And hopefully those building blocks will help explain some of the benefits and challenges we talk up front. And finally, we're going to end with some tips to think about when you're building with both these tools. So let's start with the benefits. So first of all, what is Rabbit? At a very high level, RabbitMQ is a general purpose message broker based around message queues designed with a smart broker passive consumer model. And why do people use it? So this is a tweet I saw recently where customers had open source RabbitMQ users been using it for almost 3 years. And it really gets to the heart of one of the first reasons people use Rabbit, which is it's mature, it's stable, it's a really strong open source community. These are things that are helpful when you're running production systems. Additionally, this is just a snapshot of the wide and extendable support that Rabbit has, both for the client libraries, as well as plugins that both ship natively with it, as well as community plugins. There's also a range of protocols that are supported here. So there's wide and extendable support, both from the core team as well as from the community. People use Rabbit also because it has some really best-in-class management systems. There's a management dashboard that ships with it, as well as actually this is a sneak preview of RabbitMQ 3.8, which shipped last week, which ships with a pre-built Grafana dashboard, as well as Rabbit has quite good diagnostics and health checks. I was going to go to the live. There's a live view. Just imagine that's live. It's too risky to switch to a web browser. Ask me later. We're going to talk about the building blocks a little bit later, but I do want to highlight that another reason people use Rabbit is because of the powerful routing capabilities it has. And this is captured here by the exchanges and bindings. And those are sets of rules about how messages should flow through Rabbit. And you can bind exchanges to exchanges. There are many different types of exchanges. And when you stick it all together, it gives you an amazing amount of flexibility to route things through your topology. And we'll come back to that a little bit later. A couple other things on why people use Rabbit. So it's really easy to scale by adding and removing competing consumers on a queue. It can be configured for consistency, high availability, low latency, high throughput. So we're going to talk about this in the tips, but the number one thing you can do is think about what does your application need, and then how do you configure Rabbit to support that. Another 3.8 plug that I'm going to give is cluster rolling upgrades with feature flags. So it allows a rolling cluster upgrade to the next minor version without requiring all nodes to be stopped before upgrading. It's a really exciting improvement in 3.8. It supports strict ordering, again with a new, either having a single consumer on a queue or a new 3.8 feature, the single active consumer. And I missed one, which is that it's easy to get started. As well as we've seen people use Rabbit for a whole set of wider use cases than what you would initially assume it's used for. And I think that's partly because of the extendability and the extreme flexibility it has.
Well, what is Kafka? This is, well, there are a couple of definitions that come to mind. One is more technical in nature.
Oh, sorry.
And thanks. So distributed and partitioned commit log with messaging semantics, right? It is highly distributed systems, it's based on commit log, but it gives you messaging semantics of pub/sub model. The other definition that is published on Kafka's website is that it is a distributed real-time streaming platform. Now, when I first read that, the curiosity kind of started, arising and started, hey, how can you have a log-based system that is real-time streaming, right? Doesn't make sense, right? Log-based systems are slow, real-time systems are supposed to be fast. How does it work? Remember this part, we're going to revisit this part when we get into the building blocks section, okay? But let's take a look at why industry is embracing Kafka. The number one reason is it has extremely high throughput with required data guarantees. It can scale massively. You can add brokers to a cluster. Multiple brokers, I've seen like enterprises using more than 150 brokers. That's not an unusual thing. Ability to replay events, it's a log-based system. You can actually replay the whole set of events that you want. De facto standard for streaming platform, it has powerful streaming KPIs, streaming APIs available called K-streams and K-tables. It also has ordering within a partition, strict ordering within a partition, not across the entire topic. Broad ecosystem in terms of picking up data from source, putting data into the target systems. And overall, if you look at the wider range of use cases, it could be used in event-driven microservices, log stores, streaming, event sourcing, change data capture. And if you look at it, in enterprises, it is becoming the core of their data integration architecture. So Kafka is becoming that. This kind of highlights the overall picture. On the left-hand side, we have source, connect source. You can take the data from a variety of sources, use Kafka topics as an intermediate store, and then use the connect sync to load the data in target systems, and messaging APIs and streaming APIs. We're going to focus on the streaming APIs later in the demo later. So when to use each?
So first, let's talk about Rabbit over Kafka. So the first scenario, as we talked about, there are many benefits to each, and we're going to talk about the drawbacks in a moment. But there are a couple scenarios where, given the benefits, it does make more sense to use Rabbit. The first is, Madhav just went over a couple of the really distinctive and super-powered features that Kafka has. If you don't have some of those strict requirements, like event replay, then RabbitMQ gives you greater flexibility, can meet the high throughput and real-time event processing needs with lower operational costs. And what I mean by operational costs there is both the hardware as well as the operational complexity that your team has to manage. It's just a little bit easier. It also, because of the flexibility that I mentioned in the broker, if you have evolving application requirements, let's say you're just starting out and the architectural uncertainty is high. You know you need to connect things, but you're not exactly sure how that's going to happen yet. Rabbit will let you more easily evolve as those requirements become more specific. Another key differentiator here is the decoupled producers and consumers with Rabbit. So producers will publish to an exchange, consumers declare queues, and then consume from those queues. And that means that the producers and consumers don't really need to worry or know about each other, which lets your teams really quickly and independently iterate. As I mentioned, each consumer brings its own queue, which means that the consumers don't need to worry about other consumers. Again, really good agility there. And finally, as I mentioned, because consumers are declaring their queue and choosing the messages that they need to be receiving, unlike streaming applications, they don't need to process every message. You don't need to process the messages that aren't going to be relevant. So that's a quick snapshot of Rabbit over Kafka.
When to use Kafka? It is becoming the de facto standard for streaming platform. If you need to have streaming requirements, Kafka is usually becoming the preferred choice. Extremely high throughput. It can scale, it can have parallelism because of the partitions. We're going to take a look into that. But it can scale really well. You can also have the ability to join data from multiple sources in streams. And we're going to take a look at that as well. How do you do that? So you can have concepts of streams and tables. You can have a duality between stream and table. You can have really enriching functionality that streaming API provides. And also, since it's an event-based system, the individual consumer actually can replay. It can reset the offset, what is referred to as an offset. And we're going to understand those concepts in the building blocks. But the idea here is that if you make a mistake in your processing, if you want to fix the code and go back and reprocess all the events, it's really a powerful tool. Unlike in a message queue where when you read the message is gone from the queue. In case of event log, the message stays there. You can read it as many times as you want. It's really a powerful tool when you're developing and testing your applications, right?
All right, so now the not so great stuff. So first off, let's start with RabbitMQ. I did talk earlier about how the relative operational complexity is lower than it is with Kafka. However, I don't want to make you assume that there is no operational complexity, especially in handling network partitions. It gets complicated. And another feature in 3.8 is quorum queues, which is based on RAF for consensus, which shows some improvements in this direction, but it can be challenging. Luckily, there's a lot of resources out there for you, but be warned, don't email me angry later. Queues are single-threaded in Rabbit, which means that throughput is limited by the throughput of that thread. Adding consumers won't, while I mentioned it's helpful to add consumers to scale, you can't scale beyond the compute capacity of the broker. Scaling brokers beyond 3 brokers, we're going to talk about clustering and the building blocks. But when you have a Rabbit cluster, it's really optimal to do a 3-node cluster. If you scale to a 5-node cluster, you can do that. It becomes a little bit complicated. If you scale beyond a 5-node cluster, you have some performance impacts. And that's because the Ninja transactions need to be replicated to all the other nodes. So you can imagine as you add nodes, complexity and the amount of, especially for the management plugin, which has aggregate queries, things get a little chaotic. Finally, as we mentioned earlier, there's no events replay. And it doesn't natively support stateful streaming use cases. But as mentioned previously, you can replicate some of that functionality with Reactor and the RabbitMQ Reactive API with an external state store.
Kafka is extremely powerful, extremely scalable, but there is no free lunch, right? There is operational complexity. Anyone who has operated Kafka in production at scale will know how complex it can be, right? So number one thing, it requires a separate consensus mechanism in the form of Zookeeper. So you have to have a Zookeeper and manage that Zookeeper cluster. Secondly, you have to do a very, very meticulous planning of selecting the partition count for your topics. And we'll take a look at some extreme examples of how things can get out of control with respect to selecting partition counts. Everything is log-based, so that means storage is involved. You have storage overheads that you need to worry about. You have to manage the disks. And there is not only the obvious topics that you define for your application requirements, there are also topics that Kafka creates internally to manage its own state, right? As well as manage the state of the consumer applications. It's a fault-tolerant state mechanism that provides you for Kafka streaming applications. However, that has operational overhead in terms of storage, extra storage capacity. So when you plan your storage, you have to take into account all of these factors at load, at the peak throughput scenarios that you have to anticipate, and then plan your storage capacity. Because at the end of the day, if your storage is unable to keep up, if your I/O threads are unable to keep up, you're not going to have the throughput that you thought you will have. Okay, so those overhead need to be there. Are there, you need to take into account. Careful coordination between teams writing consumer groups and producers. This is very important to understand how Kafka functions in terms of relationship between the producer and a consumer. The topic that we have in Kafka is partitioned. The consumer group can scale at the max to the number of partitions, right? And we'll take a look at that, but I'm kind of giving you an overview here. But because of that, it has an impact on the producer application as well. If you have large number of partitions, more than what the producer can actually give throughput to, your producer throughput will actually go down. So you have to make sure that the producer is able to create the messages that will fill up the buffer it has called batch. We'll take a look at that. But important takeaway here is that you have to have a good coordination between your producer application and consumer application, right? And plan the partitions accordingly. There's no out-of-box management and monitoring console that Kafka comes with, although, for example, Confluent provides you that, but it's not part of the open source Kafka. Streaming API support is excellent, but it is mainly restricted to Java. If you want to get the latest and greatest versions of the streaming API, Java is your best choice, right? And also no out-of-box solution for seamless upgrades. You have to come up with your upgrade strategy, you have to plan it accordingly, because taking down a node in a cluster has some impact. You have to plan it properly. All of these are challenges. Again, Confluent has a solution to offer here, and I'm not a Confluent employee, but I'm saying it's not part of the open source, so you have to take into account. Now, we talked about the partition challenges, right? Let's play a little game here. Okay, are you guys with me? Let's play a little game. Let us say we are introducing a topic called bar for application A. Okay, that requires a parallelism of 20 consumers. So you plan your partitions according to the parallelism requirement of 20 consumers. You do that, everything is fine. So you define a topic with 20 partitions. Life is great. You're a Kafka architect. You're excellently happy. You've done everything that your developers have asked for. Now, since some developer heard that, hey, Kafka can actually do joint stream across multiple topics. Excellent. Now, application B also has a requirement to stream events from bar. But application B already streams event from foo topic, right? And application B actually needs to join the events from foo and bar, because it has heard great capability of streaming, right? However, foo only has 10 partitions. Right? You're a Kafka architect. You promise there is a joint stream possible. The requirement here is that whenever you want to join 2 or more streams, you have to ensure that the underlying topic they represent has exactly the same partition and also the same key. Right? So life is difficult. Third application comes. Application C is also interested in event from bar. However, application C wants ordering across the topic, right? Because in Kafka, the ordering guarantee is only within a partition, not across the topic. Application C wants ordering guarantee across the topic. So application C really needs bar to have only one partition. Right? Now you're a Kafka architect, and the third developer who you promise that, hey, you can have whatever partitions you like. Now he gives you a requirement, and you can't meet that requirement. What do? You're a Kafka architect. So, fourth scenario, foo and bar events are becoming very popular, right? So application D doesn't want to be left behind and wants both the events. However, application D needs ordering guarantees across all the events. Foo events, bar events. What do? You have ordering guarantee only within one topic and a partition of that topic. But you have 2 topics, how do you ensure ordering guarantees? You end up eventually have to create, and now you're still a Kafka architect. So this is how the life gets complicated. That is why it is very important to coordinate. Now there is a solution for this problem. The idea here is that when you take into account the partition count, you have to take into account the requirements of all the consumers, potential consumers, and scale the partitions to that level. When you join the streams, make sure that you're joining the streams and they have the same key, and also the partition count is also same. I've given a reference for Kafka link over there. The sites will be available, you can follow that up. This is kind of represented in the cartoon. Our colleague Jack Van Lightly, he has kind of created a cartoon for this, excellent cartoon to represent all of this. And how this thing can be relatively easily managed if you are using RabbitMQ.
So here I mentioned earlier that the consumers and the producers don't need to coordinate. Here we have our pink porcupine saying we now have bar events published to the bar exchange, and we can see that the consuming applications on the right are going to make decisions based on what they need. So we have one application that's saying, it takes my service a long time to process each message, so I'll scale out the consumers on my queue, take that action independently. Another consumer is saying, great, I'd love bar events. I'll bind my queue to both the foo and bar exchanges, as I need ordering across the two events. So you can see here, same scenario, the complexity is a lot lower if you want people to move independently. So now we're gonna talk about the, not surprised, I knew this was coming. So we're gonna talk about the building blocks of RabbitMQ. Hopefully we'll give a little bit more context to some of the benefits and challenges we talked about. Then we have our live streaming demo. So at a really high level, this is the RabbitMQ broker. I'm not gonna get too much into it because there's lots of excellent docs on the web. But you can see that the producers send messages to exchanges. Exchanges route messages to FIFO queues and as well as other exchanges, as we talked about earlier. You can add priority to messages if you need that. RabbitMQ broker, which is depicted by the orange box, will send an acknowledgement back to the producer on message receipt if you so choose to ensure that if there's failure between the producer and the broker, the message is resent. Consumers maintain persistent TCP connections with Rabbit broker, and they declare the queues that they consume, as we talked about before. So RabbitMQ pushes those messages to the consumers. Consumers send back acknowledgements of success and failure, and the messages are removed once consumed successfully. So we talked about the exchanges. I'm going to talk through 3 of the most popular and common exchanges that RabbitMQ uses because it will show a little bit about the capabilities you can have when you want to do routing, different types of routing. First is a direct exchange. So a direct exchange will deliver messages to queues when the routing key of the message, which is in the metadata, exactly matches the queue's binding key. So on the right, you can see that we have messages. One has the images.crop binding key, routing key. The other one has images.resize. You can see the direct exchange routing those to the correct queues to be processed by the correct consumers. Here you have a topic exchange, which is delivers messages when the wildcard matches between the routing key and the queue's binding key match. So you can see here we're starting to add more complexity. One of them is routing based on errors. One is routing based on geography. You can see how you can start to layer these to really get advanced routing throughout the broker. And then finally, you have a Fanout Exchange, which delivers all messages to all queues regardless of the binding key, the routing key, or pattern matching. So quickly on high availability. So when you have clustering with RabbitMQ, you combine 3 RabbitMQ brokers, or many RabbitMQ brokers, to form a conceptual whole broker. All data is state is required, that's required for the broker to function, is replicated across the nodes. Message queues by default reside on only one node, but they're visible and reachable from all the nodes. As I mentioned, 3.8 has quorum queues, which allows you to replicate those queues using Raft as a consensus mechanism. So when I talked about how you can configure Rabbit based on your application needs, let's say your application, we're going to talk about 2 ways to resolve network partitions that lets you understand the flexibility and options you have here. Let's say you care about availability and partition tolerance. If a network partition happens, you can choose Autoheal partition handling strategy. And that means that both sides of the partition will continue to be available. And as you can imagine, the data will not be consistent. And when that network partition is resolved, the smaller side of the partition will be reset. So that data will be lost, but you had availability throughout the incident. Let's say you care more about consistency. If there's a network partition, you can choose pause minority. This means that the smaller partition will stop accepting reads and writes. You don't have availability throughout the event, but your data stays consistent throughout. We talked briefly about publisher confirms. This is when the broker confirms back to the producer that it received the message. And if the message has been appended to the relevant queues or written to disk, whatever the message is supposed to do. And then you have consumers, where the Rabbit will push messages to the consumers, which allows you to evenly distribute between multiple consumers, which can be very helpful. Consumers can acknowledge messages back to the broker. And if you're worried about a consumer becoming overwhelmed in this model, you can also set prefetch values, which is the number of unacknowledged messages that consumers can have at any one time to make sure that they don't get overwhelmed there. So RabbitMQ there are 3 RabbitMQ teams at Pivotal, so just thought I'd give you a brief overview of what's going on in each. You have the open source team in the middle. As we just mentioned, 3.8 is just out, and it has quorum queues using Raft. It has mixed version rolling upgrades. enhanced observability, so that Grafana dashboard I showed you earlier, as well as OAuth 2 support. The Rabbit for Pivotal Platform, the tile that I've talked to many of you about over the weekend, just came out with 1.18, and it has support for off-platform applications to on-platform Rabbit instances. Finally, we have Rabbit on Kubernetes, which we're actually going to talk about later this afternoon if you're interested. It's in closed beta, and the goal is to provide a great developer and day 2 operational experience with the Kubernetes native components. And the developer experience for Rabbit, here's a couple of the options that you have. You have the RabbitMQ AMQP client, which provides a low-level API to RabbitMQ. You have Spring AMQP, which is a template as a high-level abstraction for sending and receiving messages. You have support for message-driven POJOs with a listener container. You have Spring Cloud Stream, which is an abstraction over protocol and over messaging vendors. There's actually a great talk that I'm now forgetting where you can see them switching out RabbitMQ Kafka with Spring Cloud Stream, overlaying it extremely quickly. And then you have Reactor RabbitMQ, which I talked about earlier. It's a reactive API for Rabbit based on Reactor and RMQ Java client. And its functional APIs enable messages to be published and consumed with non-blocking backpressure and very low overheads, which lets you, in applications using RabbitMQ, use Rabbit as a message bus or a streaming platform and integrate with other systems for that end-to-end reactive pipeline. So I think now we have this slide, and then we have our demo. Madhav?
Well, Kafka developer experience, at the bottom layer here you see a Kafka cluster, right? On top of that, we have the core Spring API for Apache Kafka. Above that, we have a thin binder layer. It's an interface that is implemented by 2 kinds of binders. On the left-hand side, we have Spring Cloud Stream binder for a Kafka. That is part of Spring integration project, and it gives you the input and output message channels to communicate with topics, right? And that is exposed via Spring Cloud Stream to the Spring Boot application. So on top of the Spring Cloud Stream API, you create the bindings that will have the names of input and output binding channels, drive to your microservice using Spring Boot and Spring Cloud Stream. On the right-hand side, we have Spring Cloud Stream Kafka Stream binder. What it gives you is the native Kafka Stream functionality right in your Spring Boot application. So Kafka's all the rich APIs, that the streaming APIs, stateful streaming APIs, all of those are exposed via KStream, Ktable, and global creatable. And those are available as Spring Cloud Kafka Stream API to your Spring Boot application. And what does the Spring Boot provide you? It's the best way to write microservices, cloud-native microservices. So you get all the richness of Spring Boot, all the richness of Spring Cloud Stream, but with native Kafka Stream functionality, right? And we'll take a look at what exactly that means. So let's get into a demo. We'll explain the demo, what we are building here. Let's assume I'm launching a new company for insurance, which it's called JustRide. It will increase or decrease your premium for car based on your driving behavior. What this is doing here is that on the left-hand side, we have the car sending out the car events to the car events topic. And those car events topic are streamed out from Kafka to your Spring Boot application in this processor. This processor is going to check the events. It is going to apply your business logic using the K-streams and the Spring Boot and the stateful transformation. That's really where Kafka really shines. And then generate and decide whether you're violating or not, right? If you're violating, then it will send output to the other topic, stream the output back to Kafka, from where the other processor will join the violations with customer information to create a score for individual customer, right? And then it will be finally synced into a caching layer, in-memory data grid caching layer. It could be Redis, it could be Gemfire, Geode, right? Your preferred choice, which is perfectly good for in-memory data store as well as massive parallel processing, etc. Since all of this is running on Pivotal platform, you can run it on any cloud. You can run Kafka on PKS, Spring Boot applications on PaaS, and you can switch the underlying cloud infrastructure wherever you want. You can take the whole platform wherever you want. Let's take a look at the demo. For this purpose of this demo, we're going to build a smaller portion of this main, the important portion of this application. For simulating the cars, we have this car event load generator application, which is built using Spring Cloud Stream. So the left-hand side API we talked about in the stack earlier. Anyone who has seen Spring Boot project will know what application.yaml means. So we'll use application.yaml to define our input and output bindings. We'll walk through all the code. We'll use this to bind to topics and destinations, basically. On the right-hand side, which is the main business logic, which will take the events from, or stream the events from car events and process them using Kafka Stream and Spring Cloud Stream, right? And write it back to another violation topic, or stream it back to violations topic. From where another application will pick it up, which is again written in Kafka Stream, Spring Cloud Stream, and it will just print the events for the logging purpose, just to see that end-to-end flow is working. Now here, this is sort of our experience when we are building this application. We are building this application in iterations. And on the left-hand side, we have a simple POJO. It's a JSON-friendly POJO. It will have a car UUID for identifying individual car, its location, latitude, longitude, and the speed it is driving at. The message key is UUID of the car. The idea here is that when you're processing the car events, you want to absolutely make sure that defining the violation is done per car, so that my violation doesn't go to Zoe's violations, right? So it has to be ordered processing for a particular car. So we have to have a message key so that the partitioning will happen based on that. The guarantee that Kafka gives is for the same key, the message will land on exactly the same partition. So within that partition, Kafka guarantees ordered processing, right? With me so far? Excellent. Now, the experience that we got when we were building the Kafka Stream applications is that when you're building the K-Stream applications, just writing the streaming logic is not enough. You have to pay really, really good attention to the model. And this is based on the experience that we personally went through. And JSON friendly is obviously needed, but also the model can be self-aware. It need not be a simple POJO. It can be a self-aware data model. When we say self-aware, what does it mean? It means that the model has to know how to manage its own state. If the model is intelligent enough to start managing its own state, your processing logic can become much easier. If you don't do a good modeling, data modeling, then your processing logic can be really, really messy. You may still be able to get there by brute force, which is what we did in the earlier iterations, but that logic is not good. It's not performant, it's not efficient, it's consume more resources, and also not maintainable. So it's important that you pay attention to the state management. In this case, we have 3 functions. We're going to walk through the code. So why don't we jump right into the
Can we do it?
Yeah.
Great. And so this, we're doing this live code demo with Kafka because of some of the capabilities they have.
Sure.
And yeah, 1 second. And stream processing. But Madhav will be presenting a Rabbit streaming example at Rabbit Summit in November. So if you're European-based, come to that or catch the video online. We just had time constraints, so
Yeah.
there we go.
Thanks, Zoe. So let's walk through the YAML first. Application YAML. On the top here, we are defining the Kafka binder properties. When you are doing the Kafka streaming applications, you have to define the SERDE, serializer, deserializer, right? So Kafka has to know what is the default serializer, deserializer. So we are saying that, hey, use this default serializer, deserializer for default values. Then we will go ahead and use the Spring Cloud Stream constructs to define the bindings. Here the binding is based on the interface we looked at earlier, the binder interface. The binding represents an input or output something, right? Either channel or K-stream. Input, if it's a Spring Cloud Stream processor, then input binding will represent the input message channel. If it's output, then it will represent an output message channel. If you're writing a K-stream application, then the input will refer the input K-stream, output will refer output K-stream. These input and output, they need to bind to a particular topic or particular destination. In case of Kafka, the destination is always a topic. In case of RabbitMQ, the destination is always an exchange. So here we'll say, bind this car events out, which is used by our load generator application, bind it to the car events topic, and our processor logic is going to consume the data from this car event. So we're calling it car events in, right? And the processor application is going to send out the violation events out on the violations topic. And the downstream application that is going to print the violation is going to consume the data from violations in. Is the code visible to the back of the room? Not visible? No? How do I change the view?
Zoom.
Where is it?
Don't ask questions you don't know the answer for.
All right.
Try command plus.
All right. It's well. Yeah, I'm doing that.
I think you should do it. Here, can I try one thing? Try presentation mode.
Where?
View. Down.
Excellent. Thank you. So, and in the end, we are going to have defined this consumer group. Kafka has this concept of consumer group, right? Because it has to group all the consumers together because the partition assignment happens within that consumer group. Why do we need to do that? Is because in this particular case, usually you will write individual streaming application in a separate Spring Boot, but for the demo purpose, we are joining them together. So our speed check processor as well as the downstream application, they are all in the same application. That's why we have to identify the consumer group for each of those applications, right? All right. So let's look at the other code. The car generator logic, which has this binding here, which outputs the data to this particular destination, car events out, and creates a message channel, output message channel. That output message channel is used using enable binding. That's a Spring Boot annotation. Enable binding, and then the important operational part here is I'm randomly creating the POJOs for car events and sending them. The most important part here to remember is that I'm using a message key as a car UUID. That will ensure that when the messages go out to Kafka, they will land in the same partition for the same car. So there will be ordered processing over there. That's the most important part here. Let's take a look at car event. It's a simple POJO, nothing surprising here, nothing fancy here. Simple POJO with get put operations. We don't need this anymore. We don't need this anymore. And we don't need this anymore either. Now, let's go and check the bindings for speed check. This is the binding that the speed check processor application is going to use. It has car events in as a K-stream. So input is via K-stream, output is also via K-stream. My input K-stream is based on the string as a key and car event as a value. Output is based on a string as a key and violation event as a value. The processing logic is implemented in the speed check. So what we are going to do in the first iteration is we are just going to run and explain what is happening. And then we'll do a live code later on for the same logic that we implemented so that we all can learn. Here what I'm doing here is in the class I have to enable binding for that binding. Just use the enable binding annotation. Write the stream listener, write the send to. Stream listener is basically for input, send to is for output. And based on that, I have the return value and the input value. The Sathe is necessary because I'm going to perform a stateful streaming transformation. When you do a stateful streaming transformation in Kafka, in the Spring Boot application, for resiliency purpose, that needs to be materialized somewhere. Now what Kafka does is, without any developer overhead, it is going to maintain that intermediate state into a resilient data store, which will be backed by the Kafka topics. So in case this application crashes, that intermediate store can be restored in another consumer instance without developer having to do anything. That's a really powerful thing. So your traditional microservice is not exactly stateless anymore. That's the thing to watch out for. But yeah. Now we define the Sathe for that because we need to tell this materialized view how to serialize and deserialize the data. Sathe is basically serializer or deserializer. So we have to tell the materialized view how to serialize or deserialize the data. Then we start the processing of this application. We'll do the group. I will explain the code when we actually drive code. We're going to run the code now and make sure it works, hopefully. All right. OK, it's not going to work because I don't have the Kafka. Surprisingly, it's running. OK. All right, what is happening now is it has started generating the events, and the violation has occurred here. Unfortunately, I don't have the mirror here, so I have to wait.
You can see the car events coming through. The cars are identified by their key, and their speed is identified on the right. Anything above a 60 within a 30-second window is a violation. So we're counting the violations as they come through. So that's the raw data. Madhav, you want to talk about that?
Now, let's look at the violation. The business logic is that if you violate the speed more than 2 times in the 30-second window, only then we will count it against you. Otherwise, we will forgive you, right? So if you see, every violation that is being showed here as an event has count 3 or more. Now, if you are lucky, we will see another excellent behavior of Kafka that will keep the window alive. What is possible is that your processing for that 30-second window has already happened, but the event for that window arrived a little late, right? It is possible that the consumer of the application, which is your streaming application, has done that 30-second window streaming, but the event that was supposed to arrive in that 30-second window arrived a little late. Kafka will accommodate that, reprocess that aggregation, and put that event back into that 30-second window. So it's a live 30-second window. And that is, again, as I said, backed by the internal store onto the Kafka. If we are lucky, we'll see that behavior here. Let's see.
Yeah, you can see there the violation check for the car 3 has count of 3, so it's a violation there.
Yeah, look at this one. Okay, look at the violation here. Yeah, violation for car 1, right? When this window was processed, the count was 6, right? The window processing has already been done, but another event arrived for car 1, and it actually meets your speed, it exceeds the speed threshold. So it went back into that window and recomputed that particular count. As you see here, the window has not really changed. The same window is there. You see that? That's a very powerful feature that Kafka gives you out of box. So if you're writing the streaming application, it gives you a lot of abstraction that otherwise you don't, otherwise you'll have to deal with on your own. That's why Kafka is becoming like popular to replace what were known as Lambda architectures. Are you familiar with Lambda architectures? Okay, so Kafka is starting to replace those as well now. Now let us take,
I was just going to say, let's look at the business process.
Yeah, and let's talk about the violation event, which is the model that we talked about, the rich model that they understand itself, how to manage itself. Let's take a look at how the object is created. The object creation, when it happens, when the new event is created, it creates an array list to take the car events that are coming in, and also take the timestamp when the window was created. If you add a new car event, at that time it will check whether that car event is violating the speed or not. If it does, it will increase the count and add that to the list, right, and return itself. And when the closing happens, it will actually just take that n times naught and return itself. This is a state management operation that the model is enriched with. If you don't do it here, you will have to manage to do that somewhere else. That's why it is important to pay attention to the model. Now, on the downstream application, this is your downstream application where we in violation check binding, and we're just taking the events from the violations topic and just printing them, just to make sure that the end-to-end plumbing is working. It's already working. We see that violation check messages are also coming in, right? So now what we'll attempt to do is we'll build a streaming application together. So what I'm going to do is working code. Wish me good luck because I've never done this before. Mm-hmm. And it's even more painful because I have to look there and type here.
We could try and mirror it. Is that worth it right now or no?
Yeah, it will be good to mirror so that I really can't do that.
This is just a technical interlude.
Take a break. Try to absorb whatever we have discussed so far. We have 70-minute session, so plenty of time.
Make friends with your neighbor.
Yeah. Try to stream ideas with them.
All right, we should have mirroring now, and then let's pull up your codes. Great. Okay, so do you want to talk about the first 3 lines you have there, Madhav?
Yeah, the first 3 lines are basically just creating the logging instance. I want to make sure that I log everything. Windows store is what I'm basically using as a materialized view, which will be persisted, fault tolerant store, and the window size is essentially 30 seconds window. That's what I'm going to consider. So let's start writing the code, and we'll learn it together. The first thing I have to do is stream listener, speed check binding dot car events in. So that's my binding for the input events, and then send to output stream. I want to use speed check binding dot violations out.
So there you have a K-stream in and a K-stream out.
Yeah, K-stream in, K-stream out. And I have K-stream here, the key type is string, the output type, model type is violation event, speed check, and K-stream in. String again is the key, which is car ID, and car event is the model of the input stream. The first thing that we would like to do here is we would like to take the car events, iterate over it, and make sure that we are actually receiving the events. So what we are going to do here is, it's a for each operator that Kafka stream provides. And what we're going to do is just log it.
the key value there.
Log the value dot toString. Very simple, nothing fancy here, just to make sure that it's actually getting into this one. The next thing that is important here to remember is that we have to create a Sathe. So Sathe.
And that's the serialization, deserialization.
Yep, Sathe. I think the advantage of the IntelliJ IDE is that it's so smart. But if you're not paying attention, if the similar name class you happen to choose, entire streaming application will go down. So I'm going to be a little slow here.
I have some of our most common mistakes on my phone.
Thank you.
I'm not texting my friends in the audience. All right.
All right. So this is our Sathe. We want to define violation event Sathe and create new JSON Sathe and say that, hey, the class type is violation event, and use a new object mapper. So that's our violation event Sathe. This is we're going to use in the streaming application. Next thing is we're going to define the stream for the output car event. So we'll do this later. Let's not rush to it. All right. First, let's do the processing logic first. So first thing first, we have to make sure that we are processing all the cars in sequence. So a particular car in the sequence, all the events for a particular car in sequence. Car ID 1. All the events for car ID 1 are processed in exact order. Otherwise, you will have a messy situation. For that purpose, I'm going to do group by key. That will ensure that car 1, all the events are processed in order. Car 2, all the events are processed in order. Secondly, we want to ensure that there is a window happen. That I want to, once the ordered messaging ensured, I want to make sure that I'm having a tumbling window. It's not a sliding window, it's a tumbling window. 30 seconds, 30 seconds, 30 seconds. So I'm going to use the time windows of whatever the value we defined here. Window size milliseconds. So, okay. Here is the most important critical part of your streaming application. I'm going to do aggregation. This is going to be a stateful transformation. Okay, and this is where I make maximum mistakes. So, all right. So the first thing first, we have to initialize the model. The first thing, what is it that we have to initialize? Second thing is we have to tell how to aggregate it. So key, car event is my input. Car event, and then violation event. And this is going to use lambda functions. Are you familiar with lambdas? Okay, awesome. So what I'm going to do is I'm going to call violation event, add car event, and pass this event, car event, as an input to it. So this is where we take advantage of rich model which is self-aware. The next thing is the difficult part, materialized
dot. There you go.
String is the key type, violation event is the value type, and then window store of bytes and byte array
Great.
as window store.
So what are you doing there, Madhav?
Okay, so this is where the magic happens. This is the business logic of the aggregation. Rest of it is the plumbing to ensure that the stateful transformation that you're doing, the intermediate state you're doing, is resiliently managed. That is why it is important to materialize this entire view, and we're going to materialize that. It's not yet finished. So with key Sathe and our with key Sathe, Sathe's dot string, because our key is of string type, and the value is of violation event Sathe type. So we are telling this materialized view, hey, your key is of string type, so make sure that serialization deserialization happen from the bytes to the string, and for the value use violation event Sathe, which is our JSON Sathe. So treat this byte array as a JSON and make sure that you convert to JSON and from JSON to bytes. So it's important to get this right. All right, and then we'll close this one actually. Yeah. So what we have so far here is, as you see here, the grouping has the stream, K stream became a K grouped stream because we did the grouping. Windowed, after applying the windowing function, it became a time windowed stream, and after applying aggregate function, it became a K table. So Kafka gives you this stream table duality, right? Stream is a continuous stream of events, table means it's a snapshot. It will remember the last value for that particular key, right? And gives you the stream table duality paradigm without having to do anything extra. So gives you that. And what I'm going to do here is map values. I don't want to have the model open just like that. So what I'm going to do is I'm going to use the model to alter its state. I'm going to say again v close the window. So we are letting the model know. If you see here, what is happening here is the streaming application is intelligently interacting with the model, not just using the model to get put values, but interacting with it. And let the model decide what to do on closing the window. Let the model decide what do you do when you add a car event, what do you do when the new car is initialized, new event is initialized. So that is how the model and the stream, they actually go hand in hand. Now if you see, it is still a K table, but our return type is K stream, so we have to convert now. We converted stream to table, now we have to convert table to stream. Does it make sense? So we'll just call toStream operator. We're not yet done. Well, we're still not done yet. Now what it has happened is, so far it has taken into account all the events, all the violation events, even when the count of violation is less than 2. Our business logic is, if you're violating more than 2 times, only then count it against you. So we have to filter out all the unwanted violation events. V dot get violation count more than 2. This will ensure only those violations or only those drivers are counted where they are violating the speed more than twice in 30-second window. Make sense so far? Everybody with me? All right. So filtering has taken place. If you see, notice here, it is still a windowed stream, and our return type is stream, K stream, not a windowed stream. So what do we do here? We have to convert that windowed stream to a regular stream, and for that we have to use an operator called select key. Now in the select key operator, we pass on the key and value, again use lambda here to just get the key. That finishes the stream processing. How big is the code? 47 to 57. Exactly 10 lines of code. A massive transformation has taken place, real-time streaming application without using any external state store. Right? That's where the Kafka really shines.
Which return violations.
Yep. And now we have to turn the violations and oops. All right. So we have taken into account the violations now, and we have to return the violations. So what we are doing here is restoring this thing into violations and returning the violations to the downstream application, so it will be streamed back. If you are interested, what we can do is we can actually just log the events locally to make sure that, again, for each operator comes in handy, we make sure that it is what we are intending to send is actually there. So again, we log info v dot toString. Hopefully, the code should still run and produce the same output. Well, technically, the code is still running, so it's producing the same output. We haven't recompiled the code yet. All right. So we're going to stop the code. All right. Yep. Let's see. All right. The load generator application has started sending the events, and it has started receiving the event on the processor, which is what it is printing right now, if you see. And we have started capturing the violations. Big round of applause for me. Thank you.
Spontaneous round of applause.
Thank you.
Well done, Madhav.
Thank you. So now if you see here,
Yes.
take an example of this behavior. We are lucky we will capture that. So UUID 4 car has 3 counts of violations. And if you are lucky, we will see that it will arrive again in the same time window. Well, one more event has come up with the speed of 40. So it has processed that event, but if the speed is below the violation, it kept the violation count the same. But let's take an example. Here it is. So take example of this one. In the same time window, another car 4 event came. This time it is exceeding the threshold of the speed, right? Speed threshold. And this time it actually went ahead and increased the count to 4. So the window processing was already completed, but the event arrived little late. But the event was supposed to be in that time window. So the Kafka stream took the event back there, did the whole processing which we are supposed to do, and did the magic. Writing this on your own in your own streaming API, creating your own streaming API, without needing any streaming cluster, like if you write like Spark or if you are dealt with Spark, I have not done it, but it's a separate cluster, right? So you don't write any cluster here. You just write a simple Java code, Spring Boot code, and it just works. That's where the power is. Now, with that said, that completes my live demo, my first live code experience.
You can't ask for another round. Okay, go ahead.
Thank you. Thank you. Thank you. Let's take a look at building. How much time we have?
We have about 15 minutes.
15 minutes?
No, we have about 10 minutes.
Okay. So
We talked
literally,
about the building blocks of Rabbit. Now we're going to talk quickly about some of the architecture that makes up Kafka and makes what we just saw
Right.
possible.
yep, we're going to skip some of the building block slide, but this is the most important one. You remember when we introduced Kafka, what did we say? We said Kafka is a log-based system, and it also gives you real-time streaming, which we already saw, real-time streaming platform. So how can you have a log-based streaming, log-based system giving a real-time streaming? First of all, whenever you have a sequence, it's a sequential I/O. It's a sequential operation. The reads are sequential, writes are sequential in Java, in Kafka, right? Whenever you have sequential I/O, the disk performance is tremendously better. When you have random I/O, disk performance goes down. But here it's a sequential I/O. Secondly, Kafka makes extremely smart utilization of operating system features, such as page caching and zero copy send files. What that means is that when you're reading and writing the data, and as long as you avoid those evil scenarios, right? Old broker, out of sync broker, unpatched broker, old client libraries, massively lagging consumer. There are some, really bad consumers, etc. Right? You avoid those evil scenarios, you will get in-memory performance, because what happens is your reads and writes never actually go to the disk. Operating system takes care of all of that. Kafka doesn't do anything over there. Kafka just uses that. So your Kafka streaming, Kafka broker, the idea here is that you use maximum messages that should reside in the memory. You have to provision a good amount of memory for that to happen, so that maximum memory is available for the page cache. How does it work here? Let's say you have the ACK equal to 1. This is not a 101 session, so sorry for those people who do not have the basic knowledge of Kafka. I was supposed to cover some of the building blocks in detail, but we don't have time. So ACK equal to 1 will mean that only the leader of the partition, out of multiple replicas, one particular replica is nominated as a leader. Only leader of the partition need to send acknowledgement that I received the message, right? AC equal to 1, sending the message to broker, broker writes to file system. In file system, the file system takes the data, writes it to memory cache, and sends the confirmation to broker that I got the message, I got the data. But the data is not actually returned to the disk in a synchronous way. The data is cached over there for some time, and bulk data is written asynchronously to disk IOPS. So disk IOPS are never part of the call path for this producer of the message. Similarly, for consumer of the message also, when you're requesting the message from it, unless you are lagging too much behind, the message is already available in memory cache. It has one more, because of the zero copy send file, it has one more advantage. It can send directly from the, it's available in the kernel space, it sends directly to the NIC buffer and send it over the wire to the consumer. So it avoids even the Java heap on the return path. And it's again, zero copy send file is again an OS feature. Kafka doesn't do anything there. Kafka just takes advantage of the existing operating system features. And there's a very good video here, and in the previous slide I have kind of given a link over there for a Confluent Kafka Summit talk, which one of their employees had done. Excellently explained behavior and why Kafka is so fast. I've given some links. This is a broker and cluster architecture. One of the brokers is nominated as a controller, and there is a zookeeper which maintains who is the controller and which broker is the leader of the partition, right? Which broker has the leader of the partition. And controller has some functions. It manages the shutdown, it elects the leader of the partition, and communicates that election to other brokers in the system. So it has some functions over there. There are things to watch out here. If you're using Kafka, certain versions, very old versions of Kafka, there could be problems. It could be problems not only in terms of operation, but also in terms of performance. So I'm going to skip through some slides. Skip through some slides and go straight into the tips. One more thing, consumer group is an important concept to remember, right? The partition assignment happened to individual consumer group, instance of a consumer group. If you have only one instance in the consumer group, all the partition will go to that. If you have exactly as many number of partitions as the consumer instances, there will be one-to-one mapping. If there is a third consumer, it's of no use because it will not get any partition. If the consumer crashes, right, consumer instance crashes, it will reassign the partition to available consumer, right? So whenever the reassignment happens, partition reassignment happens, entire consumer group stops. That means patching a consumer group could be a challenge. Real-time patching could be a challenge. So if you are having a CI/CD pipelines, that will just do a rolling upgrade of the application in real time without, you have to be careful over there. Now let's take into the tips for efficiently using Rabbit.
So at this point we've talked about, given our upfront goal of explaining a little bit about the benefits and challenges of both solutions, when to use both, and the building blocks behind those architectures that make those benefits and challenges real, hopefully you know when and where you want to use each of these. So there are a couple tips we're going to give you here on when you're using RabbitMQ Kafka. The first thing here is, I'm actually going to start with the third one. This talk encompasses a very, very deep area, as you can see by our time constraints. There's lots of resources out there. If you want to read more about this, would recommend both the RabbitMQ resources that we have out there for using Rabbit efficiently, as well as actually there's a blog series by Jack Van Lightly that goes more into depth of some of the comparisons here. So overall tips for using Rabbit efficiently. The first, as we talked about in the benefits section, is clarify the requirements of your application. You can configure Rabbit for high availability, high throughput, low latency. There's a whole range of things that you can see it achieve, but it's important that you know up front what it is that you want to do. We see a lot of customers immediately turn on, data safety for everything, which does impact performance, despite not needing data safety for everything. Also, we talked extensively in the beginning about the benefits of Rabbit's monitoring, especially with the capabilities in 3.8. Be sure to monitor your Rabbit if you want to have a good experience. For queues, a happy Rabbit is an empty Rabbit. So we showed in the architecture the queue structure. Keep your queues short, make things a little bit easier. For performance, we recommend you use in-memory, non-mirrored queues. For HA and data safety, the quorum queues that we mentioned in 3.8 is a great feature. For producers and consumers, use multiple consumers if consumers are slow or if there are too many producers We talked about this and the ability to scale out competing consumers. It's really helpful. If messages can't be lost, make sure you're using acknowledgements. And for resource use, every connection, channel, queue, costs memory, and CPU. The harder the work, the more they are, the more resources are required. And if you really care about throughput, it's good to have as many queues as cores on the underlying nodes. Finally, for performance, keep messages in memory. If messages can't be lost, ensure you use prefetch values. This is, again, a really small snippet in the no time we have left, so please Google around. There's lots more resources, including from CloudAMQP, on how to efficiently use Rabbit.
Well, next, tips for Kafka. Tips for efficiently using Kafka. Number one thing, if you love your data, set ACK equal to 0. It will ensure that your data is replicated, and only then the confirmation will go to the producer. If you want a balance between reliability and latency, then you have to use ACK equal to 1, which is what we saw earlier. Hotkeys, it's a very important thing. Because partitioning works in a really, it's a very important strategy that you have to take into account. If you have hotkeys, what can happen is you may have hot partitions. Let's say out of 100 keys, there could be 5 keys that are retrieving bulk of the data. So wherever those 5 keys land, those partitions will be hot partitions. Rest of the partitions will not be having any throughput or having any activity. That is not a good strategy. Ideal topic is a balanced topic with evenly balanced workload across all the partitions, right? So for that, if you have such things, consider separating these hotkeys into a separate topic. That will be a good idea. Producer efficiency, batching happens on the producer side. I couldn't cover that in the building blocks. It's not a one-on-one session, as I said. So the broker API does batching per partition, right? So the best throughput scenario is that multiple messages are going in a batch together. So it will give you best performance. The optimal batch size will give you a good balance of throughput and latency. Linger is when the sender will not wait for the batch to finish or batch to fill. It will send it anyway. So linger of 5 seconds is usually a good thumb rule to start with. If you want a higher throughput, increase your batch size. If you want to consider latency, then you consider lingering the low end frequency or lowering the batch size. So batches will fill up faster. If you have large files to send, I'll just ignore that part for now. We have a lot of other things to cover. Tips on using keys. If you're using null key, that's the best way to ensure that Kafka will do the round robin across multiple partitions that are there. If you have null key, that means that the data can be evenly distributed to all the partitions in the cluster. If you need the stream processing, then you cannot use null key. Stateful streaming transformation, ordering transformation, you cannot use null key. You have to ensure that the data for same key lands exactly in the same partition, because the ordering guarantee is only within a partition. How do you do that? Well, if you don't need real-time ordering, you can consider taking the data, streaming the data from a topic, and storing it into another store and having the timestamp of the message within the message body or within the message value. And use downstream application to establish the ordering in a data store later on. We can discuss this later on after the session. It's a little more intense topic, but you can create creative architectures to achieve best of the both worlds. Best of Kafka's performance due to null key and establish the ordering later on in the downstream side. Yep, a lot of Kafka's performance depends on the availability of the page cache, so make sure the maximum memory on the node is available for the page cache. Kafka is a Java, so you have to make sure that the garbage collection overheads are not there, right? You have to watch out for these. Watch out for things that can have adverse impact on Kafka. If you have extremely large messages in a same topic, right, it may block the consumer if it is not configured with the right buffer size. It will not know how to consume that large chunk of data at once. So consider, yep.
I think we're actually out of time.
Out of time.
Thank you all for coming. Please find us later. This talk will be online. Again, there are many resources. And a huge thanks to the many, many people who helped us with this. Thank you.